The Dirac's delta function or the unit impulse function. Consider a function as shown. This is the time window where time is plotted on the x-axis and the signal is plotted on the y-axis. So on the time axis we begin with an initial time ti up to a final time tf. Let's consider this function of a shape like this, starting from ti till a particular time tau equal to t1. It remains 0 and then suddenly it jumps up, remains constant, and then again becomes 0. The width for which it remains constant is given by delta tau, and the height of this is given by h. If we impose a constraint on the area of this rectangular shape, let's say area is A, that's equal to 1. So area is h into delta tau, which is equal to 1. If we reduce delta tau but keep the area the same as equal to 1, the height of the rectangle is bound to increase. If we continue doing this, as delta tau tends to 0, h will tend to infinity. And the resulting signal that we get will be like a spike or an impulse, which we represent as delta tau minus t1. This is because it occurs at tau equal to t. This is the Dirac's delta function. We define it like this: delta tau minus t1 equal to 0 whenever tau is not equal to t1. So from ti to t1 it is 0, and from t1 plus delta tau to tf it's again 0. But it is equal to infinity when tau equal to t1. So you can see this impulse, it's equal to. But all the while, the area under this rectangle, it has to be equal to 1. So the integral from minus infinity to plus infinity, delta tau minus t1 with respect to tau is equal to 1. Now suppose we take a function f tau and we multiply it with delta tau minus t1 and take the integral. What should happen? So in this region ti to t1, f tau gets multiplied by 0, and in the region from t1 plus delta tau tf, again the same thing happens, it becomes 0. But in this interval during delta tau, it gets multiplied. The value of the function is f at t1, and it gets multiplied with the area, which is 1. So the answer becomes equal to f t1.